Right, good morning, ladies and gentlemen. How's it going? Good. Quite quiet. Sounds like everyone enjoyed the beer event last night. How's it going? Slightly louder. Okay, fine. All right. So my name is Richard Warburton. I work at a company called Option that develops and sells low overhead production profiling tooling. And this talk's called Fantastic Performance and Where to Find It. So, what are we going to be talking about in this talk? Well, firstly, we're going to talk about what we mean by performance and the kind of overall approach we're talking about here, about doing a more scientific, more methodological approach to trying to solve and understand performance problems and reducing the amount of guesswork that we have to deal with in our lives. Then I'm going to go through a few kind of simple examples of just using profilers to identify performance bottlenecks in kind of simple toy application, and we'll see how we can apply those lessons not just in isolated synthetic examples, as I'll show on my laptop in this talk, but also how we can apply those things in real production systems and apply those ideas more generally. And we'll just kind of wrap them up at the end. So I use the term fantastic performance in the talk title, which is obviously a good decision because there's a lot of people in the room. But what does fantastic performance actually mean to me? Because lots of people, especially in London, work on sort of sometimes quite performance-intensive systems, like high-frequency trading systems, sometimes very kind of high-scale internet services, sometimes quite esoteric systems I don't think many software developers deal with. But what does being good for performance mean? And for me, it's often about meeting your business objectives, right? It's about having software that keeps your customers and your users happy, that doesn't have kind of slow, awkward page load times that annoy people. It's about having software that doesn't use up compute resources inefficiently, so that keeps your infrastructure costs down and also helps make the planet a little bit more environmentally friendly as well. It's about having software that scales out effectively rather than just falls over when you've got more than a few users on your system. So it's about having software that doesn't have performance as a reliability problem for users as well. So that might sound in some way like a low bar for fantastic. Is that really fantastic? Isn't that just kind of okay? But if you think that, just think about how frequently you hit services that don't meet that bar, that go down under load, that have really awkward, annoying, frustrating page load times and things like that. So for me, it is actually often about being fantastic. And I think when you're talking about different performance in terms of software, there's a couple of different views you could take on it, a couple of different approaches, big picture things that you can think about. And firstly, a lot of talks that you see at conferences are about architecture and frameworks and tools, right? If you want good performance, you need to go reactive. You need to go web scale. You need to use a NoSQL database or some architectural choice. You need microservices to scale out. Who's heard those kind of messages repeatedly over time? That's most of us, right? Yeah? Yeah. And sometimes you get these fantastic, beautiful architectural diagrams and big pictures drawn. But this talk isn't about that kind of approach. It's about a different approach to understanding performance problems, which I think is a more scientific approach. It's about measuring what's going on in your system in a more architecturally agnostic way. It doesn't really matter necessarily exactly what framework or technology you use. It's about thinking about how we can, with simple approaches, work with lots of those different things and understand problems. And I want to show this as being not something that requires you to have some kind of magic touch or anything like that. Just something that's very, very simple, something that's very approachable, something that's very repeatable, and something that we can think about in a bit more of a scientific manner, a bit more of a concrete manner, rather than everything being one neat trick, or you've got to do this to scale out. A lot of the talk here I'm going to be giving is talking about how different we can use profilers and tools to understand performance problems. I've done a few talks before about how profilers work under the hood. If you're interested in those kind of low-level details, which personally I am, there's a lot of other talks. This isn't really about that kind of talk about how things work under the hood. It's more about how you can use things and understand the results from these tools. But if you are interested in learning more about how these profiling tools work under the hood, then I gave a talk at DevOps UK last year on production profiling, what, where, and how, which you can find online. Okay, so let's have a look at a few kind of more profiling examples and about what profiling does for us. So what do we mean by profiling? Well, profilers are tools that tell us where the main user of some kind of resource in their system was. Okay, so what was using up your different CPU time? What was using up the wall clock time in your system? What was allocating objects? What was eating up the memory? Okay, so they're tools that let us measure and understand what's going on in a production system. And by having these kind of tools, we can challenge our existing mental model with some data. Now, scientists have a very strong concept of having a hypothesis-free investigation, right? So you set up some you might set up a hypothesis to test, but when you're testing that hypothesis, you're trying to avoid thinking about assuming ahead of time whether it will be true or false. You're trying to figure out how you can capture data to measure and see what the problem is. And I think that's what we should be trying to do here with profilers, not just taking our existing assumptions around behavior. Because when we all write code, we all have a mental model in our mind, right, of what's complex, what's slow, what's fast, what's doing what from reading and writing the code. And these tools allow us to kind of challenge that and establish, is that true, is that false, what things are going on. But profilers aren't necessarily the first tool, even though I'll be showing them in this talk, that you necessarily want to look at. One of the first things that's always very useful when trying to understand about a production system without having huge amounts of hypotheses about what's going on inside is just basic CPU metrics. Now, a lot of people have fantastic, nice systems for gathering these, graphing them, all sorts of things. I've got a bit more of a traditional, old-fashioned approach here. I've just printed out running VM stat from my laptop. And VM stats, you don't necessarily need to know all the details of it. And VM stats one of these delightfully unfashionable command line tools, right? But it's worth drawing your attention to just having a look at a few key stats that you can pull out of this. I mean, if you've got those metrics and graphing systems, then use them. But what are these key metrics that are worth thinking about when looking at your system? Some of the most important things are just basic CPU time measurements. User time, system time, idling, wait, and steal for what's going on in your system here. And looking at the ratio of things like how much time you're spending inside user space, so that's your application code, versus system time, which is where you're spending time in the kernel, versus time where you're idling and your system isn't doing very much, are really useful. You can say if you're spending lots of time in user space, then trying to add more parallelism to your system is not going to improve things. If you've got an interestingly tuned and set up system and it's not performing very well, and you see a lot of steal time in your system, then that's possibly a hardware problem. So steal time, which, is anyone familiar with what steal time means on CPU measurements? So steal time is something where you're running a virtual machine or a container inside a modern environment. Like a lot of cloud services do this all the time. And other resources, other VMs running on the same CPU, on the same hardware, are actually having time that's stolen away from your steal time, a noisy neighbor type problem. So looking at metrics like steal time are often very useful when you're deploying to systems like AWS, especially if you're using the smaller node sizes, smaller instance sizes, as they tend to have a lot of time stolen from them. But let's assume for the moment we aren't going to look at the metrics for the different examples I'm going to look at, because I've already had a look at them beforehand, because I just want to focus more on profiling. So let's move on to those examples. If you're interested in having a play around with them after the talk, I've put the code up on GitHub, this performance, github.com/option/performance problems example, and the slides will be available after the talk, so you can have a look at it there. So let's have a look at our first example of a little bit of code. So again, a very simple program that has a little CPU bottleneck in that is doing a lot of computational work. So what I've done here for this program is I've downloaded a bunch of data about house transactions in the UK. So the government makes available all this data about what transactions are going on, who's buying what houses, well, not who, but what the prices are for house price sales and all the transactional data. And I've got that data here. And I've put together a simple HTTP endpoint that will let you search through that data. So, for example, I've got a little service running on my local host. I can search for whether these transactions contain a certain string. I am going to use Cardiff as the string to search from, as that's the city I was born in, that's where I'm from. And it will return you a list of transactions in a JSON format. When it starts up, there we go. That meet this search string, that have these search strings within them. So, you can see it might be searching the primary addressable object name. So these are kind of like house name number things in the street, locality, town, city, district, things like that. Okay? And if you look at the way this code is implemented, then we have a house resource. So just a drop wizard type application. And we're going to hit this endpoint. We're going to call the search method on some underlying query. We're going to process a little bit of data with the streams API, pulling that sales data out, finding whether it's in a certain query string, and looking that up. Okay. So in order to see what's going on, I've got a simple house search benchmark here. So what I'm just using, just in order to put a bit of load on this system on my laptop, is AB, which is the Apache HTTP server benchmarking tool. I'm going to run C-4 means running on 4 threads, and then I'm just going to run a couple of hundred transactions, a couple of hundred queries here in the background in order to see what this system is doing. Now, the benchmarking approach I'm taking here is not necessarily the most scientific of benchmarking approaches, because this talk isn't really about how to write the best possible performance tests. It's more about how you can understand what's going on in your system once you've got some load on there. And in fact, later on I'll show you that performance testing isn't necessarily the key thing to be concerned about. And I'm just running this benchmark in order to make sure that we can get some measurable outcomes and see what's actually going on with the system. Now, this first search may take a little bit of time because it's not terribly well optimized, but AB gives us some latency numbers at the end. So this is a latency histogram that AB is producing us. And it's telling us that half of our requests completed within 864 milliseconds or less, and all of them completed within 136 or 1.3 seconds, basically. Okay, so what I'm going to go to now is our Opsian profiler here. So you could investigate and profile these things with a lot of different tools. I'll mention a few other tools later on. This is one that we have. And we are in London, and the time is, I'm going to just make that later on. And let's look at what our first DevOps benchmark run did with the profiling data. So this is a flame graph that we have on screen. Has anyone used flame graphs before? Is familiar with flame graphs? A few people, not many. That's great. So that's new for most people. So flame graphs are a way of visualizing what application code is actually doing. Okay? And flame graphs are a kind of visualization that puts each method that's being commonly used within your system within a box. So if I just zoom in here so you can read what's going on a little bit more clearly. At the top of our flame graph, we've got javalang thread.run. So that's the run method of threads that kicks things off. And within this system, we're using Jetty as a web server. So we've got a bunch of methods flipping there through Jetty code. Now, because this profiles your entire application, we might want to filter down our thread groups a little bit to ignore things like application startup, because it was just a little benchmark tool here. So if I apply a thread filter, we can remove all the other threads that aren't starting with the name DW and then some number. That's what the question mark is there. So that's what Drop Wizard names its core thread pool where it runs most of these applications. Now, within a flame graph, you see each method lower down the flame graph here is a method that's called by its parent in the flame graph. So higher up methods call lower down methods, just like regular stack traces. And the width of the box within your flame graph is a way of visualizing how much time that method and its children used up. So we can see a lot of these boxes here all have very, very wide sizes. And if we zoom in on them, we can see they're all using up 95%, 100% a lot of time. But it's worth thinking when you're trying to understand these visualizations, not just how wide the boxes are on flame graphs, but how the shape of this graph changes. That's what visualizes, that's what should draw your eye to. So it's as the boxes start to narrow towards the bottom of the flame graph, this is where we want to understand where the performance is actually coming from, because all of these other methods at the top, where they're basically as wide as their children, that means the methods themselves aren't using up very much time themselves. It's their children which are using up some time. So let's kind of scan in further down here where we get to our application code. So that house resource.sales search, that was the top method in our Jersey application. Sales query.search, that was the method I showed you where we were doing the filtering and the search. And we can see that most of the time within that code is used by a method called salesdata.getSalesData. Okay? Not necessarily within the self time of the search. So what is that getSalesData method doing? It's calling a method called readSales. And readSales is doing a few interesting things here. Firstly, it's using this CSV-reader method. And it's also doing things like parsing local dates, splitting up strings. So it looks like it's doing some string parsing. So let's go and have a look at that code, shall we? So we've got our getSalesData method here. And what's that getSalesData method doing? It's a bit weird, right? It's one of these cases where we should have a getter in our application that should just be returning some kind of field, but it's a lazily initialized field. So our getSalesData checks if the sales data field is null, and if so, it initializes it. Otherwise, it returns the sales data that it's read. But what we can see here is actually there's just a slight error in our code. Instead of initializing the sales data static field, we've initialized a local variable called sales data. Okay? Kind of simple accidental mistake that we could all make very easily. And another thing to note here is now, because we're lazily initializing this static field, we could potentially call that from multiple threads. So I'm just for now going to make that a synchronized method. And if I just rebuild that package, and I've passed devox2 at the end of that. So that's a different agent name for this run of the script. So I'm going to use that later on to see what's going on there. Great, so we've started up. So if I run that same house sales search, remember it's taking us 800 milliseconds in the 50th percentile. You are totally correct. I still have the exact same problem in my code, don't I? Well, let's call it 3 now. So now I'm initializing the variable within my program. Things do run notably faster, about 10 times faster. Okay, so things are running a wee bit faster. Thank you very much, whoever called that out to me. And let's see what's happening with our profiling data from our DevOps 3 run and see what's going on there. We can see, if we zoom in now, that previously, where our sales query.search method was spending all its time reading that CSV file, that has pretty much disappeared from our profiling data entirely, and it's all spending time performing the search itself. And this is a search that goes through a collector streams pipeline, and because streams API is lazily evaluated for intermediate operations, it's a terminal operation that ends up having initially be the entry point within a profile. And as we look down, we can see most of that time is spent actually using this contains ignore case method within our application code. So let's go back to that code and see what that is doing. Well, we've got our contains ignore case method, and it takes the first field, makes it to an uppercase string, and checks the second. The query string is the uppercase as well, and it puts a contains within it. And if we look at what our profiling data says that's spending time doing, it's spending nearly all of its time making strings their uppercase versions and very little time actually performing a contains in order to perform this case-insensitive contains method. Okay. Now, thankfully, I've got this Apache Commons library that has just a contains ignore case method in here as a import. So if I rerun that with using that contains ignore case method rather than the more dumb two uppercasing both of those strings and doing the contains within them, and rerun the little benchmarking script, we were at 71 milliseconds beforehand, and we're now down to 55 milliseconds, so a bit of an improvement. What does our profiling data tell us on this one? Well, it tells us that a fairly similar amount of time is being used here by contains ignore case. It's a little bit cheaper than the previous operation. We know this has sped up our system because we had the measurement earlier that said the latency had reduced, but the contains ignore case method is still taking up the bulk of our time here, so it's still the thing we should be looking at. Now, conveniently, I know that actually this comparison that's trying to ignore cases is actually pretty useless from a bit of domain knowledge, because all the input data provided by the government on these house data prices is actually in capital format anyway. So I could just say to uppercase on the input string, call that our query string, and because all these fields are uppercase to begin with, I could literally just say field.contains query string, apply a bit of domain knowledge there, and rerun and rebuild the system. And once this is up, we can rerun our benchmark. And we're way faster again, 25 milliseconds there from 77. Okay? So that was a simple example of a kind of CPU-bound bottleneck. So we use flame graphs. We could see where within that flame graph it was narrowing down, where the time was being taken, and we removed that bottleneck. But whilst profilers are often used for removing bottlenecks for things that are CPU-bound, a lot of bottlenecks in systems aren't directly CPU-bound. They're not about necessarily improving the efficiency of the system. They're often about making better use of the system, removing situations where we aren't really using all of our CPU time. So I've got another example here where my demo application has got a few kind of little bank account data points in it, and it has a legacy bank service that I'm also going to run on the current machine. The legacy bank service is a bit of a dummy application here. You'll request the legacy bank service and ask what was the balance for some bank account for a given user on the legacy bank system, and we'll merge it into our application's bank account system. Okay, so if I rerun that start there, and I've got a merge accounts benchmark script here that I'm going to run. Well, if I wait for the application to start. Okay, so merge accounts takes a little bit of time to run, so instead of boring you too much with what's going on there, let's have a look at the code for what it's doing, and we'll pop back to the data and see what's going on in a sec. So when we have that merge accounts endpoint, we call this merge balance from legacy account, and we're running this code here. We are running all of these transactions under a big lock where we do all our bank transfers under. We talk through to this external system on the legacy bank proxy. So what that does is it just uses the Apache Fluent HTTP client to talk to another web service, executes that response, gets their balance back, updates the bank balance and deposits some money in from the old system. And because these things potentially could be running concurrently with other operations, that's why we ended up with this big transfer lock at the top to try and avoid any race conditions on that. And performing these merge accounts operation ended up taking 28 seconds on our machine. So, what happens if we go and take a look at what this system here is doing? So I think we want to get to Devox 6. Lovely jubbly. Now, we get a bit of a different CPU time graph here. And this is a CPU time graph that is not massively useful in terms of what it's telling us, because this benchmark, I know from having had a look at it, analyzing the metrics beforehand, is actually not very bottlenecked on using CPU time. It's spending a lot of time waiting around, idly doing nothing, the kind of information you could get from those CPU metrics. And that's why we want to think about using a different type of profiling timing data when we have those kind of performance problems, when we have blocking-related problems rather than CPU time problems. And what I've got here is a wall clock-based profiling data rather than just a CPU time-based profiling data. So the difference between those two things is that CPU time-based profiling is measuring the time that these operations spent actually executing on the CPU, actually performing computational work. So that is scaled precisely to what's actually going on the CPU time. Whereas wall clock time is based upon measuring the kind of beginning to end of operations type time. So that will tell you, include things when it's operating off CPU, when it's blocked, when it's doing locks and things. But this often provides a very different kind of view of what's going on. So what's the biggest thing that's eating up our wall clock time when you look at our system? Well, actually, we've got a bunch of threads in this thread pool, and we aren't hitting all of them at the same time. So a lot of this time is being spent with our server socket waiting to accept a new TCP connection. But that's not really the bottleneck here, because we just don't have many TCP connections. So If we look at what our bank method here does, we've got our merge bank from legacy bank account method, which we see takes up a lot of the remaining time. And in both times, we can see a narrowing down of the flame graph between that and its child node. Remember when I said when you see the flame graphs kind of narrow in visualizations, that's a good indicator that there's a lot of self-time going on within that method where they start narrowing in or start splitting up. That's where you want to look at things. The child method that's taking up a lot of wall clock time is that get bank balance method that was talking to the external service. But actually, it's the self time which is eating most of that time. So if we go back to our code here, we can see it's not really doing very much in this method. It's calling our get bank balance. It's looking up some database DAO. It's depositing the money and persisting. Now, we know that these methods aren't taking up much of the time in our system, because if they were, we would see them as child nodes in that flame graph, which means the thing that is taking up time is the code actually executing within the method itself, this synchronization based upon a big lock. It's a lock contention problem. And I have an alternative locking scheme here. I don't really want to go too much into the details of that, but that basically has a lock per person, so it allows for a much more fine-grained locking strategy. Now, obviously, there are lots of other locking strategies that you could apply in this situation. For example, striked locks, for example, where you have a certain number of locks and you allocate based upon a hash of that person to the lock. Either way, it's a way of reducing the lock contention and not having all these operations contend on the one big lock. And if I rerun my benchmark with this different locking strategy, then we'll find that the time it takes in order to measure these things drops dramatically. So from 28 seconds down to 8 seconds. So about a fourfold speed up there. A bit more than fourfold, actually. Okay. So let's go back into this system and take a quick look at our different profiling data and see what the latest system ends up being bottlenecked on. Well, we can see actually we end up with a lot of things here that are calling socket input stream. If I read down there, socket input stream dot socket read 0. So in the JDK, that is a native method that's reading data from a socket. And you're waiting on reading that data from a socket. And if we look up through the stack trace, we can see what kind of resource you've ended up looking through there. So for example, we've got a get bank balance method on our legacy bank proxy. So what we're actually doing here is sitting there, spending time waiting on talking to an external system, an external service, which if you're doing an SOA service, an SOA-based architecture, or microservices-based architecture, is a very common thing to do, right? You end up waiting on a lot of external services quite a lot of the time. Now, the solution in that problem is to speed up this other service, which I am going to do through a wee bit of demo magic. So in my demo case, I can just provide a different argument to that external service, and it will be much faster. Okay? Now, in reality, maybe you're maintaining that service yourself and you need to reapply this methodology to fix that service. Maybe you are maybe you have another team and you need to bribe them with some kind of baked goods or confectionery in order to prioritize speeding up their system. Maybe you can just make them understand through the power of your compelling arguments, which you can do because you can say, my service is definitely bottlenecked on this service. And now we've removed that bottleneck on the external service. Our merge account system runs much faster. We've gone from 28 seconds down to 1 second for running all that code. All right. Cool. So those were kind of very simple examples that I could run on my laptop in a conference talk in 20 minutes and have a look at how you can see those visualizations and how they can apply, and that methodology can apply to solving some application problems. But real-world problems have a number of different issues, right? They're a lot more complicated than these kind of synthetic approaches. So let's have a look at some of these different problems that we have with more real-world systems and how we can overcome those problems so we can still apply the same methodology, the same approach that I talked about just then, but on a bit more of a realistic system. So firstly, what I showed then was very, very simple benchmarking scripts that weren't necessarily super realistic in terms of what an actual production system is doing. And writing performance tests that replicate that behavior from a production system that's realistic in terms of the different users, hitting different endpoints at the same point in time, hitting the right distribution of loads, getting the data right, getting the right hardware, the same stuff as you're using in production, timing operations, not just hitting the endpoint as fast as possible as A/B does, but perhaps hitting operations in periodically over time through things like Pareto distributions for generating workload. That's really hard to get right, okay? And my solution to that kind of problem is don't do it. Performance testing is a very time-consuming and complicated operation to get exactly right, and a much better approach for solving and understanding these kind of performance problems is measuring what's going on in a real production system. You've got your real hardware in there, you've got real data, and you actually know what your users are doing in terms of their workload, which you don't have as an option in terms of your performance tests, so it's very, very hard to get right in terms of performance tests. But in order to implement this correctly, you need to have profilers that have low enough overhead to be used in production. So I'll mention a few examples later. On this slide, in fact. So obviously, I work at Opsian, and we have our own profiler, which was the one I was showing there. But there are certain open source profiles which are low enough overhead to be run in a production setting. Async profiler, honest profiler, the perf mapper agent stuff, flight recorder. These are all can all be very, very low overhead if you run them at the right kind of sampling frequency. But they may not do other things that we're going to talk about. Problem 2, intermittent issues. So quite frequently, you have performance problems that aren't like just a catastrophic swarming of your production systems that go on nicely until you fix it, like the benchmark run I could do. You might get little bursts of traffic here and there. Maybe a gambling site that gets a load of traffic on Cheltenham races going on. Maybe a food delivery site that gets loads of traffic on a Friday evening when people are more likely to order takeaway than they would do on a Wednesday at lunchtime. Maybe you're doing loads of e-commerce work and you get big sales season discount type things. Sometimes you get periodic issues that happen within a system, like bursts of traffic on a weekly or a monthly or an annual basis, rather than just a constant burst. And sometimes you can get timing issues, so things that happen here and there periodically, but just kind of random to spot. And I think the way you can apply profiling approaches in order to address these kind of issues is through continuous profiling. So continuous profiling is not just profiling with a low enough overhead that you can run it in production, but just leaving profiling switched on all the time and gathering that historical data so that you can see what's gone on in your system. That enables you to look after the fact, post hoc, and see what actually happened during this problem. And it also enables you to perform comparisons. So you don't just look at profiling data necessarily when you see your system under load, but you can see what it's doing under load versus what it's doing normally. Sometimes seeing what it's doing when it's not under load under a profiler will reveal lots of very surprising things to you about your system. For example, I've had clients, we've profiled their system, and they've realized that what they're spending most of their time doing is just throwing exceptions and then catching them. It's something you wouldn't necessarily spot all the time, but they had somewhere where they had a catch and they'd commented out the catch because they thought it was fixed or they didn't want to see something in development somewhere, and then it turns out they were spending loads of time, and you kind of see that information in profiles quite easily. Then there's also the situation of infrequently used code. So the most common case, I think, for businesses who have this kind of situation is things like a sign-up process, right? So if you've got people who are coming to your website, you want your sign-up process to be really smooth and really nice, yeah? Because if you lose customers on your sign-up, that's very expensive for you as a business. It's costing you money to potentially try and acquire those customers. So if you're losing them on the sign-up, they're not going to transact with you. You're not going to make any money off them. But if you look at what a lot of systems do, rarely is the sign-up process, or for example, login pages, the main driver of traffic in a system. Often it's things like seeing product pages or catalog type information, for example. So how can you understand that with a profiler? Profilers are often very good at telling you what's using the system, what's busy at that point in time. And a lot of people, I think, throw away production profiling because they want to see a small one-off problem in, say, a sign-up page or in one of those few endpoints rather than what's going on in the whole system. And the solution to that problem is the ability to query your historical profiling data, slice it, dice it, and be able to filter profiles by given methods and by given threads. Okay? Now, if you've got a continuous profiling system, you've got loads of data points about your system. So even if you have a few slow endpoints, you'll probably have some data in your system telling you what they were doing when they were slow, stuff that you can exactly and precisely look at. And you don't necessarily need a huge number of samples of data to look at if you're looking at very precisely the problem that you want there. So, for example, being able to look up the method name of an HTTP endpoint where you see that data coming through and filter the samples that your profiler is taking you by that endpoint name immediately allows you to narrow down to the part of your application that has that problem in. Okay? And as I say, even if it's not code that's being run that frequently by your customers, if you're continuously profiling over time, you can still see what it's doing. And kind of problems 4 and 5 are related. So profilers, traditional desktop profilers, are very difficult to use in a production setting. They're difficult to use because of access rights. A lot of them are based upon the idea that your profiling UI is running on the same machine as your JVM that you want to profile. And in practice, it may be running in a different data center, in a different building, in a different country. I was going to say on a different planet, but that's not really true. Some organizations have internal barriers between developers having access to production. They may be, for example, regulatory Chinese walls that say people who operate systems can't be the same people who write code systems. They may be more kind of social, cultural barriers. But either way, you may not have direct actual access in order to be able to practically use a profiler in a production system. And then there's the fact that most desktop profilers aren't really designed to be able to attach to a system when it is under load or when things are going wrong. If you take things like, say, JStatsD and JVisualVM, and you connect to a very heavily loaded system, especially if it's doing things like running out of memory, you hit a problem where it just can't connect. It times out trying to connect, and it doesn't work. The other problem related to access is also a problem of scale. What if you've got a bunch of different machines and you want to be able to access those different machines? How do you look at the different machines and how do you understand where those are going on? And the solution to both of those kind of problems is decoupling that profiling process from the visualization and the historical data. So, having your JVM agents connected to the JVM itself on startup, so you don't have to have this break glass, emergency attached, let's hope nothing goes wrong, fingers crossed process, but something that's already in place, proactive, and you know works. And then aggregated data so you can look at that data after the fact and see it through, for example, a web UI in a different country. Cool. So, let's wrap up this talk. We should have a couple of minutes left at the end for questions, maybe. So firstly, I'd like to give thanks to a number of people. Now, the effort that's gone in, I would say, by people to making low overhead profiling work on Java and the JVM is huge. And there's a lot of people outside who've done lots of great work in this space. And if you're interested in learning more about profilers and performance analysis, a lot of these people have blogs or Twitter, useful information that you can get from them. Brendan Gregg works at Netflix, invented the flame graph visualization, written a book on performance analysis, very smart guy, lots of information. Andre Pangin wrote Async Profiler. Jeremy Manson open sourced some various ideas around low overhead profiling. There's a Java perf mapper agent as well by Johannes Rudolph. And obviously Oracle have a couple of teams who've done a lot of work on these things. It would be remiss of me not to mention these people. And also, these things are great, these people are also great resources of information that are really useful to learn more about. So why were we doing this again? Well, we said we wanted to have the technical and business benefits of faster software. We wanted, responsiveness and reliability in our systems to get happier users. We wanted cheaper infrastructure to make our accountants happier, and scalabilities to make the VC's dreams come true. And in order to achieve that, we were doing that through profiling and measuring a production system. So there are a few kind of key tricks that we used here, looking at CPU time on our system when we were CPU bottlenecked and seeing what was really precisely causing the kind of algorithmic slowdown, the workload there. Wall clock time when having more low CPU blocking, lock contention, external service, waiting for disk I/O type problems. Flame graphs are an interesting visualization for seeing how time is being spent within an application. And the key thing to look about flame graphs is not where they're big and fat and the shape looks the same, but where they start narrowing or splitting up. And that's where when they're narrowing is where there's self-time. When they're splitting up is when you can see time being chunked off into different methods. Looking at profiling can be very useful for understanding when there are problems in other systems, not your own as well. Socket read as a tail node in a wall clock profile is normally talking to an external service, or if not an external service, it'll be talking to a database and performing some database query. And by looking up the flame graph stack trace, you'll see where that hits your code, and that vector tells you what bit of code you need to change or what service you need to talk to. Same thing with if you ever have bottlenecks based upon reading files as well. But it won't be socket read 0, it'll be reading a file. The overall methodology and approach we talked about in this talk was a data-driven optimization of the dominant consumer, which is a very fancy way of saying, find the biggest bottleneck, fix the biggest bottleneck, iterate and repeat. Be data-driven, be agile, be experimental. Don't just assume that going reactive and rewriting everything will fix all the problems. And hopefully what I've tried to convince you in this talk is that understanding what your system's doing in terms of its performance characteristics is not some kind of crazy operation involving taming a magical beast or a wild animal. It's a more scientific approach. We can measure what's going on, we can apply a methodology, it's repeatable, it's scientific. And as long as we do that with the right methodology and the right tooling, we can find and fix problems in a very kind of simple and applicable way. That's the end of the talk. Thank you very much. I hope you enjoyed it. 2 minutes left for questions. So if anyone has one question or two questions, you can put your hands up. Hey.
Historical data is very helpful, of course, but it's lots of data. How often do you look at it? How often do you check it? And how do you measure all this bunch of data?
That's a great question. The question was, how do you measure and when do you look at that historical data? And I think these kind of problems for understanding performance and solving those problems are a business requirements driven process. So if you've got so you're keeping historical data for a couple of reasons. Firstly, you might want to look at a problem that has been, say, intermittently going on in the past. So in that case, you would have spotted that there was a problem there, and then you can look at those particular points in time in your historical data where that problem happened and learn what was going on that point in time. Another reason to do historical data is you've just had an outage. Maybe you had an outage overnight, everyone in the team was asleep. You just look at last night's data. And the third reason to look at historical data for me is a kind of comparison between what your system is doing, say when it's going wrong or when it's going right, and seeing how that behavior changes under load. So that would be a situation where maybe you have a problem now and you want to see, was it really like that before we did that deploy yesterday? And things like that. So those are the kind of times when I would look at historical data. Okay, one quick question I have time for.
Is there any way to measure the performance impact of profiling?
So yes, there are two answers to that. Firstly, using another profiler. That's lower level. We at Option have done that, so we have had clients who've got, for example, application performance monitoring tools. They've used our tool, and our tool has told us your biggest user of CPU time is this other APM tool. If it's a Java agent, we can tell you that. The other way of measuring those things is if you have a kind of client-consumer-based view upon your response times or latency within your system, sort of CPU metrics, and seeing how those things change over time. For us, we've had clients say we literally can't measure the difference. And I think for that slide earlier of the low overhead open source stuff, you can configure those tools in a way that they'll be very low, low enough that most people couldn't measure it using the measurement they have available. But those are the approaches that I would take. Thank you very much.